All right, page 88. We're going to calculate escape velocity for planet Earth using the data that we know about planet Earth. So, we know that the radius of the Earth is 6,378 kilometers. We know that the mass of the Earth, we already did this in the lab, is 5.9 times 10 to the 24th kilograms. We're just going to round that to 6.0. And we know what the universal gravitational constant is, 6.672 times 10 to the negative 11. So all we're going to do is just plug in some numbers and see how this works. So our formula, V escape, equals square root of 2gm over r. Now we're just going to plug in our values. All right. So that's going to equal 2 times 6.672 times 10 to the negative 11 times the mass of the Earth, 6.0 times 10 to the 24th kilograms, over the radius of the Earth, and we have to use meters, not kilometers, so that comes out to 6.378 times 10 to the 6th. Okay. There. Okay. Now it's just a matter of crunching the numbers. So we go 2 times 6.672 times 6, and we get 80.064 times 10 to the 13th over 6.378 times 10 to the 6th, and that equals 12.553 times 10 to the 7th. And this time we're going to go ahead and cheat. We're not going to get into fractional exponents. So we'll go ahead and cheat, and we're going to change that to 125.53 times 10 to the 6th. And that comes out to 11.204 times 10 to the 3rd meters per second, or 11.204 kilometers per second. And that equals 25,052 miles per hour. And yeah, that's escape velocity for planet Earth. All right, pretty straightforward stuff, nothing all that fancy. All right, moving on to the next page. We'll just continue rolling here. So now let's see what happens to escape velocity if we compress the Earth down to a sphere 15.85 millimeters in diameter. And I picked that number because I happen to have a little steel ball that is exactly that size. So what we're saying is, what would happen if we could somehow compress the Earth down to something this size? And we kept the mass. We're going to keep the mass of the Earth, 6.0 times 10 to the 24th kilograms, but we're just going to squeeze it down into an object this size. What happens? Well, we've already done most of the math here. All right. Well, we've already done this top row, and that's not going to change. And so that comes out to 80.064 times 10 to the 13th And if I have a diameter of 15.85 millimeters, that means that I have a radius of 7.925 millimeters, which is 7.925 times 10 to the negative third meters. Remember, we have to use meters. All right, so that becomes my new denominator, 7.925 times 10 to the negative third. All right, so now we go ahead and divide these, and we get 10 to the 10.103 times 10 to the 16, which equals 3.178 times 10 to the 8th meters per second. Now that number should jump out at you. 3.178 times 10 to the 8th meters per second. If you need a little reminder, how's this? C equals 3.0 times 10 to the 8th meters per second. In other words, that's the speed of light. That is greater than the speed of light. So the escape velocity required to leave the Earth compressed into a little ball this size is greater than the speed of light. That means not even light can escape the surface of this object here. And we've already established that gravity does affect the pathway of light. We covered that in general relativity. So what are we describing here? This is a black hole. And if we could turn the Earth into a black hole, this is how big the Earth would be as a black hole. Even though it's not possible, because we have to start with a mass that is 3 solar masses worth of neutrons to get a black hole. That's minimum to get an actual black hole. But if we could suspend reality just enough to imagine making the Earth this small, this is what the Earth would be if it was a black hole. That's how big it would be. That's the Earth as a black hole. Now, what's in a black hole? We'll pause here. I'm going to clean the board, and I'll show you some basic outlines of what we know about black holes.